Acid-base equilibrium, acid-base neutralization reactions. In this tutorial, we will be going over the definition of a neutralization reaction, strong acid and strong base neutralization reactions, weak acid and strong base neutralization reactions, and strong acid and weak base neutralization reactions. An acid-base neutralization reaction is a reaction where an acidic solution and a basic solution are mixed together to produce water and a chemical salt. Neutralization reactions between any strong acid and strong base occurs until the substance in the lesser amount runs out. The acid or base in excess determines the resulting pH of the solution. Strong acid, strong base reaction. Determine the pH when 35.0 milliliters of a 0.150 molar solution of chloric acid is combined with 25.0 milliliters of 0.200 molar lithium hydroxide. The chemical equation for this reaction is HClO3 plus LiOH yields LiClO3 and H2O. The net ionic equation here is H plus 1 plus OH minus 1 yields H2O, as H plus 1 represents our strong acid, the OH minus 1 represents our strong base, and since they are in a 1-to-1 ratio, they will neutralize each other to form water. It is important to notice in the example that the volumes of the two solutions, 35 milliliters and 25 milliliters, are not equal. Therefore, we need to utilize the dilution formula to calculate the molarity of the hydrogen ion concentration and hydroxide ion concentration when initial volumes have been combined. Remember that the moles of solute remain constant even though the combined volumes will increase. As a result, the molarities of both the hydrogen ion and hydroxide ions will decrease compared to the initial molarities of each. So let's see what this looks like. We're going to start by solving for the hydrogen ion concentration after the solutions are mixed. So we're going to write the dilution formula, noting that the V2 right here is going to be the total volume of both solutions. Next, we're going to substitute the numbers from the stimulus into the formula, where the initial molarity of the strong acid is 0.150 and the initial volume of the acid is 35.0 milliliters. Then we're going to complete the calculation. Notice again that the 60 milliliters is coming from the combination of the 35 milliliters and the 25 milliliters. Then we're going to complete the calculation solving for M2, where M2 is equal to 0.0875. Then we're going to solve for the hydroxide ion concentrations after the solutions are mixed. So we will write the dilution formula. We will plug in our values, where the initial molarity of the strong base is 0.200 molar, and the initial volume is 25.0 milliliters. Then we're going to solve for M2, and once we complete the calculation, the answer is 0.0833 molar for our hydroxide ion concentration. The next step is to use these calculated molarities of the combined volumes to determine pH. To do this, a BCA table is utilized, where BCA represents before, change, and after. Before the neutralization reaction occurs, the initial concentration of hydrogen ions is 0.0875, and the initial concentration of the hydroxide ions is 0.0833. A product of the neutralization is water, but as a liquid, water is not considered when calculating pH. The lower concentration value of the hydrogen ion and hydroxide ions is completely consumed during the neutralization reaction. This is represented in the change section of the table. We observe that in this example, the hydroxide ion concentration is completely consumed during neutralization. Therefore, the smallest molarity is the limiting reagent. The hydrogen ion concentration is in excess with a calculated concentration of 0.0042. This remaining amount of hydrogen ions can be used to calculate pH. So we'll use the pH formula of pH is equal to the negative log of the hydrogen ion concentration. We'll substitute in our hydrogen ion concentration from the table and determine that the pH of the solution is equal to 2.37. Let's do another example. Determine the pH when 35.0 milliliters of a 0.200 molar solution of nitrous acid, HNO2, is combined with 25 milliliters of 0.250 molar sodium hydroxide solution. The Ka of nitrous acid is 4.6 times 10 to the negative 4. The chemical equation for this reaction is HNO2 plus NaOH produces NaNO2 plus H2O. The net ionic equation here is HNO2 plus OH minus 1 yields NO2 minus 1 plus H2O. We'll notice that Na has been removed from this net ionic equation as it is a spectator ion. When we examine this net ionic equation, we recognize that HNO2 is a weak acid, the OH minus 1 is going to represent our strong base, and the NO2 minus 1 is our conjugate weak base. Similar to the previous example, the volumes of the two initial solutions are not equal, 35 milliliters and 25 milliliters. The dilution formula is used to calculate the molarity of the HNO2 concentration and the OH minus 1 concentration with the combined volumes of solution. The difference here is that a weak acid is involved rather than a strong acid. So the calculated M2 represents the concentration of HNO2 as the majority of the acid exists in the molecular form based upon our Ka value. So we're going to start by solving for the concentration of the weak acid after the solutions are mixed together. We're going to write the dilution formula, knowing that V2 is going to equal the total volume of both solutions. We're going to substitute the numbers from the stimulus into the formula, where the concentration of our weak acid is 0.200 and the volume associated with the weak acid is 35.0 milliliters. Then we're going to complete the calculation and determine M2 to be 0.1167 molar. Then we're going to solve for the concentration of the hydroxide after the solutions are mixed together. So we'll write our dilution formula, we'll substitute the numbers from the stimulus into the formula, where the concentration of our strong base is 0.250 molar and the volume associated with the base is 25.0 milliliters. We'll complete the calculation solving for M2 and determine M2 to be 0.1042 molar. The next step is to use the calculated molarities of the weak acid and strong base to determine the pH of the solution. To accomplish this, again, we're going to use a BCA table where the HNO2 concentration is 0.1167 and the concentration of the hydroxide is 0.1042 before neutralization takes place. Two products result as the neutralization reaction occurs, NO2 and H2O. The water is not considered when calculating pH. The concentration of the conjugate weak base, NO2 minus 1, will be a factor. Prior to neutralization, no NO2 minus 1 is found in solution. OH minus 1 has the lower of the two concentrations before the reaction occurs. Therefore, the hydroxide ion concentration is completely consumed during the neutralization reaction. This is represented in the change section of the table. As the weak acid undergoes ionization to neutralize the hydroxide ions, nitrite ions are produced. In other words, for every one hydrogen ion involved in neutralization, one nitrite ion is formed as a product. That is why the value in the change section of the BCA table for HNO2 removed is equal to the value associated NO2 minus 1 gained. The amount of HNO2 remaining after neutralization is 0.0125, which is in excess. The amount of NO2 minus 1 produced as a product of the reaction is 0.1042. After neutralization, the remaining nitrous acid and nitrite ions in solution shift to establish a new equilibrium state. This is accomplished by using a Rice table. After neutralization, 0.0125 molar HNO2 and 0.1042 molar NO2-1 exist in solution. No hydrogen ions are present. Some amount of HNO2 will be ionized to form hydrogen ions and nitrite ions. We will assume that X is small based on the Ka value. Therefore, at equilibrium, the values in the race table will be 0.0125 X and 0.1042. Using the equilibrium expression for Ka, the values from the table can be substituted into the formula. So Ka is equal to 4.6 times 10 to the negative 4 equals X, which is going to represent our hydrogen ion concentration, the concentration of our nitrite ion on top, and the concentration of our weak acid on the bottom. So solving for X, the hydrogen ion concentration is determined to be 5.52 times 10 to the negative 5 molar. We use the pH formula, pH is equal to the negative log of the hydrogen ion concentration, to substitute in the hydrogen ion concentration value, so the pH is determined to be 4.26. Let's do another example. Determine the pH when a 0.20 molar solution of nitrous acid, HNO2, is mixed with equal volumes of 0.20 molar sodium hydroxide solution. Again, our Ka of nitrous acid is 4.6 times 10 to the negative 4. This example uses equal volumes of acid and base. Therefore, the dilution calculations are not needed. In the BCA table, the concentration of HNO2 from the stimulus is 0.20, and the concentration of the hydroxide ion is also 0.20 before the neutralization reaction occurs. Water is not a factor and no NO2-1 ions are present. Concentrations of HNO2 and OH-1 are equal, resulting in the complete neutralization of both reactants. As the weak acid undergoes ionization to neutralize the hydroxide ions, nitrite ions are produced. As seen in the previous example, for every one hydrogen ion ionized from the HNO2, one NO2-1 ion is formed as a product. This is why the value in the change section of the BCA table for HNO2 removed is equal to the NO2-1 form. The amount remaining after neutralization only involves the weak base, NO2-1, with a molarity of 0.20. So after neutralization, only NO2-1 ions remain in solution. The weak base reacts with water to establish a new equilibrium state. This is accomplished using a Rice table. So after neutralization, 0.20 molar NO2-1 ions exist in solution. Water is needed as a proton donor to the weak base, but is not involved in the calculation of pH. No HNO2 ions nor OH-1 ions are initially present. Some amount of NO2-1 ions will react with the water to produce HNO2 and OH-1. We will assume that X is small based on the Ka value. Therefore, at equilibrium, the values in the race table will be 0.20, X, and X. The Kb value is needed, so we will use the formula Kw is equal to Ka times Kb. We will rearrange the formula to solve for Kb, substituting the values into the equation. The Kb is determined to be 2.17 times 10 to the negative 11. Using the equilibrium expression for Kb, we will substitute the values into the equation from the Rice table. We'll multiply 2.17 times 10 to the negative 11 by 0.20 to solve for x squared. We'll take the square root of this value and solve for x, where x is equal to the hydroxide ion concentration of 2.09 times 10 to the negative 6 molar. Then we'll use the POH formula, where we'll substitute in our concentration for the hydroxide ions And when we solve for pOH, we find the value to be 5.68. The question asks for us to determine the pH. So if we have the pOH value and we subtract that from 14, we can determine the pH value to be 8.32. Weak acid, strong base reaction summary. The previous example demonstrates the point at which the equivalence point is reached. This occurs when the concentration of the acid equals the concentration of the base and both are completely consumed. pH is determined by the conjugate base reacting with water to produce conjugate acid and hydroxide ions. The reverse can occur if a weak base and a strong acid reach equivalence. The conjugate acid then determines the pH. The Kb value for the conjugate base will need to be calculated if only the Ka is given. Now let's look at a weak base and strong acid reaction. Determine the pH when 40.0 milliliters of a 0.30 molar solution of methylamine CH3NH2 is combined with 20.0 milliliters of 0.30 molar solution of hydrochloric acid, HCl. The Kb of the methylamine is 4.74 times 10 to the negative 4. So our chemical equation here is CH3NH2 plus HCl yields CH3NH3 plus 1 plus Cl minus 1. The net ionic equation is CH3NH2 plus H plus 1 yields CH3NH3 plus 1, where CH3NH2 is our weak base, H plus 1 is going to represent the strong acid, and CH3NH3 plus 1 is the conjugate weak acid. Notice here that the chlorine ion has been removed since it is a spectator ion. This example involves a weak base and a strong acid. The dilution formula is needed as the volume of the two solutions are not equal. As we can see that we have a 40 milliliter solution combining with a 20 milliliter solution. We will start by calculating the concentration of the weak base after the solutions are mixed. So we're going to write the dilution formula, noting that V2 will equal the total volume of both solutions. We'll substitute the values from the stimulus and solve for M2, which is determined to be 0.20 molar of our weak base. Next, we'll calculate the concentration of the hydrogen ion from the strong acid. We'll write the dilution formula again, substitute in the values from the stimulus, and solve for M2. So the concentration of hydrogen ions in 60 milliliters of solution is determined to be 0.10 molar. The next step is to use these calculated molarities of the combined volumes to determine the pH. Again, we will use a BCA table. Before the neutralization reaction occurs, the initial concentration of CH3NH2 is 0.20, and the initial concentration of the hydrogen ions is 0.10. The concentration of the conjugate weak acid, CH3NH3 plus 1, will be a factor when calculating pH. Prior to neutralization, no CH3NH3 plus 1 is found in the solution. The lower concentration value of H plus 1 is completely consumed during the neutralization reaction. This is represented in the change section of the table. As the weak base reacts with the hydrogen ions, CH3NH3 plus 1 is produced. In other words, for every CH3NH2 molecule neutralizing one hydrogen ion, one CH3NH3 plus 1 ion is produced. That is why the value in the change section of the BCA table for CH3NH2 is equal to CH3NH3 plus 1. The amount of CH3NH2 remaining after neutralization is 0.10, which is in excess. The amount of CH3NH3 plus 1 produced is 0.10. After neutralization, the remaining concentration of CH3NH2 and CH3NH3 plus 1 shift to establish a new equilibrium state. This is accomplished by using a Rice table. After neutralization, 0.10 molar of C3NH2 exists in solution. Water is needed as a proton donor to the weak base, but is not involved in the calculation of the pH. The weak acid CH3NH3 plus 1 was formed as a product of the neutralization reaction with a concentration of 0.10. No hydroxide ions are initially present. Some amount of CH3NH2 will react with the water to produce CH3NH3 plus 1 and hydroxide ions. We will assume that X is small based on the Kb value, which is 4.47 times 10 to the negative 4. Therefore, at equilibrium, the values in the race table will be 0.10, 0.10, and X. Using the equilibrium expression for Kb, the values from the table can be substituted into the expression. Notice that the 0.10 in the numerator and the 0.10 in the denominator cancel, resulting in X equaling the hydroxide ion concentration, which will equal 4.47 times 10 to the negative 4, which is the Kb value. Therefore, pOH is equal to pKb. To determine the pH, we will use the formula pOH is equal to the negative log of the hydroxide ion concentration. Next, we will substitute in the hydroxide ion concentration and solve for pOH. The pOH value is determined to be 3.35. Once the pOH value has been determined, we can solve for pH by subtracting 3.35 from 14. So our pH value is determined to be 10.65. Weak base and strong acid reaction summary. The previous example demonstrates the point at which half equivalence is reached. This occurs when the concentration of the strong acid is equal to 1/2 the concentration of the weak base, or the concentration of the strong base is equal to 1/2 the concentration of the weak acid. For a weak base, strong acid scenario, pOH is going to equal pKb. For a weak acid, strong base scenario, pH will equal pKa. So what did you learn? We talked about the definition of a neutralization reaction, strong acid and strong base neutralization reactions, weak acid and strong base neutralization reactions, and strong acid and weak base neutralization reactions. Need more help? Feel free to contact me. Have a great day.